Welcome to the next lecture from data formats, and today we will talk about our first graph data model, and that is the Resource Description Framework, or RDF data model. And we'll talk about how to describe data using RDF, and then we'll mention linked data and how RDF plays together or supports linked data. We have seen this diagram before. It is from our first lecture when I showed you something about conceptual modeling. We created this diagram basically to be able to communicate with various stakeholders about what is and what is not in the data we will talk about. And the advantage I told you about is that there is no connection to any particular technology or data format or data model. So we can talk about the data with business people and so on. And today we will use this conceptual model to create data in a graph data format, RDF, or graph data model. We will start with something simple. We'll start with just the class representing a data catalog. And it has three attributes: title, description, and homepage. So now we should be able to imagine how the actual data instance look like. So if we have one particular catalog, what will be in the data, right? So we'll basically say there is a thing which is a catalog. So we'll have one particular catalog. Then we'll say the catalog has title and, for instance, my catalog. We'll say the same about the description. We'll say the catalog has description, my first testing catalog. And then the catalog has a homepage with this URL you can see in the slide. Okay, so this is how a particular instance of the catalog may look like when we talk about it, right? Now let's emphasize different parts of those sentences a bit. So there is always the thing we talk about, the catalog. Then there is the way we relate it to other things, like the catalog, which is the relator. And then there is the value or thing we relate it to a catalog in the first case. So there is a thing is our thing, our catalog. And we say, which is a catalog. Three parts to this simple sentence. Then we say the catalog, again, the catalog is the same catalog, has title, and the value is my catalog. So again, all these sentences have these three basic parts. The thing we talk about, some value we assign to it, and the way we assign the value. And we can draw this as a graph. So we can say the red oval here represents our catalog. The blue catalog oval represents the type of things, the catalog type of things. So basically it can be also viewed as a set of all possible catalogs. And then there is the edge labeled, which is saying that the particular one catalog is of a type or belongs to the set of all catalogs represented in the graph with the blue oval. And we can continue. We can say the catalog, which is again the same red oval, has title, which is a different kind of edge, my catalog, which is a value. And we'll denote the value by a rectangle. Then we can add another statement. The catalog, again the same red oval, has description, which is another edge, my first testing catalog, which is another value. And finally, the catalog has a home page, which is yet another edge in the graph. And now the home page will be identified by its URL. And because it's identified by a URL, it's a thing. And because it is a thing, we can say that this home page is a page, where is yet another edge in the graph. You may note that the label of this edge is the same as the first one, which is a. And there is a new blue oval representing the type page, or as we may view it, a set of all pages. And again, you can see how these simple statements or sentences on the left relate to a graph representation. Now, we already talked about IRIs, and that IRIs are used as identifiers for things in various data formats used on the web today. So this is what we will do now. We will identify all the things using IRIs. We did that for the web page already, and now we'll do that for the catalog itself. So we'll create an IRI. It can be an arbitrary IRI, and assign it to the node representing the catalog. Now, the blue ovals, the types, are also things. So we will also identify them by IRIs. These IRIs are no longer arbitrary. They are already defined. And if you actually go to this IRI as if it is a URL, which it is, you'll see a definition of what it means to be a catalog. So this IRI actually represents a set of all catalogs, or a type which we can assign to a thing, saying that this is a data catalog. And now the same goes for the edges. The edges, the properties, are also things, because we can point at them and say what they mean, what is their label, and so on. So instead of labeling the edges with text like this, like before, we will label the edges also using IRIs. So that is what happened to the leftmost edge, representing the title of the catalog. Now the title, the edge assigning a title to the catalog is identified by an IRI, which again is the IRI used on the web to represent titles of things. And we'll do the same for the description, and we'll do the same for the has homepage edge, and we'll do the same for the remaining two, which is a edges. Well, and this almost covers what we represented as RDF. One more entity needs to be replaced by an IRI, which is the page. That just happened. So now this is almost, or actual RDF, Resource Description Framework representation, a graph representation of the data that is described by plain English on the left side of the slide. The things in the graph, the nodes are identified by IRIs. The edges are also identified by IRIs. And the values are either simple values like the text, my catalog, or my testing catalog, or they are other things like the page, or the type page, or the type catalog. Now, as you can see, this notation that we put the whole IRIs in the slide means that not many IRIs fit there. So the first optimization of this we'll talk about is so-called prefixing. So what I just did is I replaced the long IRIs with a shorter variant of those IRIs. However, this prefixed or so-called prefixed version of the IRI is or still represents the full IRI. I just omit the beginnings of the IRIs and replace them with something more human readable like RDF : or X : or DC terms : but these shortcuts, the prefixes, stand for the whole beginning of the original IRI. So these two representations still represent the same IRIs. This one is more concise, it's shorter, fits better in the slides, and is used in some RDF serializations, which we will go through later. Okay, so when we say there is a thing which is a catalog, this is a statement. And now we know that it is also a so-called triple, because it has three parts. The thing, which represents the edge in the graph, and catalog, which is either, well, in this case, it is a thing representing the set of all catalogs or the type catalog. But in the second sentence, for instance, the third part is a simple value. And we call these parts of the triple subject, which is the thing we talk about, the red part, predicate, which is the type of edge we use to connect this thing to other thing or value, and object, which is the other thing or the value. Subject, predicate, object. And now that we have introduced the notion of a statement or a triple, we can rewrite the graph we see on the right side and use it to rewrite the sentences to something which already is an RDF serialization. So we will rewrite the sentences with what we see in the graph, and we'll use RDF triples for that. And you'll see that the RDF triples can still be read the same as the original sentences. So here we replaced our first sentence with X catalog, which is the IRI of the catalog, RDF type, which is the IRI of the edge saying it is of a type, or which is a, and dcat catalog. Dcat catalog is the IRI representing the definition of a type catalog, or a set of all catalogs. And we can do the same for the second sentence. So this says the catalog has title my catalog. And the next sentence, the catalog has a description, my first testing catalog. And the next sentence, the catalog has homepage, X homepage. And the last sentence, X homepage is of a type fourth page, where fourth page is the IRI representing all pages or the type page. Right, so the original sentences, now on the left, can be rewritten as RDF data, as graph data, as can be seen on the right. And the RDF triples on the right are read the same way the English sentences, the simple English sentences are read. So this is why RDF is quite a natural way of representing data in its graph, natural graph representation. The same way the data or the things the data is about are connected to other things or values in the real world. That's why graph data models are the most natural data models, because they come directly from the conceptual representation, which reflects how things are in the real world. And this brings us to RDF, the Resource Description Framework. It is a graph-based data model. It is represented as a set of triples, which means that the triples we saw in the initial example are the triples that the RDF data model is made of. You can represent any data as triples in RDF. It will be a lot of triples, but that's how it is. And the important keyword here is that it is a set of triples, which means that there are multiple triples in the graph data model and there is no ordering relation among them. So it doesn't matter which triple goes first in some serialization and which goes second. They all together represent the graph which can be either, which can be imagined as the graph drawing, again, which we saw in the initial example. Each triple consists of a subject, a predicate, and an object. For instance, Jakub Klimek studied at Charles University. RDF was created as a W3C recommendation in 2004. Then there was one update in 2014, which was quite a minor update. So basically, RDF as we know it exists since 2004. It is important to realize that RDF is a data model, so it doesn't say by itself how it is serialized in a file. For that, we have RDF serializations. And there are 7 standard RDF serializations, which you can see listed on the lower left side of the slide. And we'll start with the most native ones today. And later, we'll talk about how RDF can be serialized into XML and JSON and also CSV. But at this moment, we'll start with something simple. So the simplest part of the RDF data model is a triple statement. We've seen that in the example, and here we have another example. It says that there is a thing which has a creator, and the creator is, let's say, an employee with ID 8574. And we can also draw this statement in a graph notation where ovals identify or represent things and edges represent the connections of those things. So here we have 2 things. We have the page and we have the employee, and they are connected using an edge which is identified by an IRI creator. The first part is a subject, the second part of the triple is a property or predicate, and the third part is an object. And both the ovals represent a thing, and in RDF we call things resources. So RDF resource is the same as thing. Now we have already seen a second type of a triple where the object is not another thing, but it is a simple value. And the simple value in the graphical notation is represented by a rectangle. So here we have a web page which has a subject, and the subject of the web page is the text education. Now, again, this triple has a subject, a predicate, and an object. However, and the node, the page, is still an RDF resource. However, the textual value is called a literal. So a literal is a simple value. We have already talked about prefixing. So we will use prefixes quite a lot. And prefixing works like this. You have the absolute full IRI, and you take a prefix, which usually is from the start of the IRI up till the last slash or hash, and you'll name that part. For instance, DC terms, like in this case. And then you use this part with a colon and the rest of the IRI. And this shortened prefixed IRI still represents the full IRI. It's just shorter and more readable by people. Now, when you see RDF data in some serializations later, you'll see that they really use these prefixes a lot. And also when you will write your own data and maybe query the data later using Sparkle, you may come into a situation where you know that the IRI you want to use is, for instance, DC terms creator, but at that time you will not know what is the URL prefix which is represented by DC terms. In that case, you can use this handy web service prefix.cc, and you can use it like in the rectangle. So prefix.cc/ and the prefix, and it will give you the most likely your IRI prefix that it stands for. This is a community managed web service. So you'll see many options of what IRIs the prefix can stand for. However, one will be the favorite and it will almost always be the correct one. So when you see a prefix and you don't know the IRI, which you won't because they are long and each one is different, you can use this service to look it up. And that's because when you use the prefixed IRI in your file, let's say, you always need to define the prefix with the prefix keyword and so on, so that it is clear to the parser which IRIs you actually mean by the prefixed version. Also, regarding prefixes, you may use other prefix names for the same URI. It's up to you as a creator of a specific file or a query how you name your prefixes. It doesn't really matter because they resolve to the same IRIs when defined properly. However, there are established or mostly used prefixes, and it is not a good idea to redefine them into something else. It will work, however, it won't be easily readable by people then, such data or queries. Right, so let's add some triples so that we don't work with just the one. And here we have three triples. We have the page, and we say that it has a creator, it has a subject, and it has a language. Now, as I mentioned, the RDF data model is a set, so there is no ordering among triples. So it doesn't say that the creator triple is the first one. It just lists them in this order on the slide, but there is no ordering. Right, let's talk a bit more about literals, because up to now I said that literals are simple textual values, and that's only partially true because a literal actually has always a textual value, but it also has a second part, and the second part is either a data type saying how the textual value can be interpreted or parsed, and that's the case here. And the commonly used data types are from the XML schema definition. I also already mentioned this in the initial lecture, that all the data formats we will talk about use the XML schema data types. And this also applies to RDF. So in RDF, we use mainly XML schema data types. And in this case, we use the XML schema date data type. We still have one triple here, which is the page was created, but the literal here has two parts. It has the textual value and a data type definition. The data type is identified by its IRI. But that's not all. When literals contain a text in a natural language and not a data type value, it is necessary to specify in which language the text is. This is because RDF is made for the web, and the web is quite inherently multilingual, so it is always good to know the languages of texts in the data. So in RDF, when you have a literal, it's either a machine-readable text with a data type or a human-readable text with indication of a natural language in the form of a language tag. The language tag gets the language shortcut from the ISO 639 standard. So if you know this one, it's the standard representation of languages using two characters. You can use it as a language tag. The most common, of course, is English, EN, and in the Czech Republic, it's CS for the Czech language. And this is also something we have already seen, because we talked about that we have a catalog which is a catalog, and we had a page which was a page. So now we have a employee which is a person. We have the employee, which is the one person, that's our resource, and using the RDF type predicate, we assign it to a set of all people, or we assign it a type person. And this type person is also a resource because everything in RDF is a resource. But because this one is meant to be used with the RDF type predicate, we also call it a class. So in RDF, a class represents a set of all instances of a given type, and it is used to indicate a type of a thing. Not always we need to identify things or resources in RDF with IRIs. Sometimes it might be beneficial to not assign an IRI to a thing. Every time you assign an IRI to a thing, you make a commitment to manage this IRI, to make sure that it doesn't change, to make sure that it stays accessible if it is a URL. And also you need to follow some rules called IRI patterns, so that the IRIs assigned to things in your dataset are assigned consistently. So for some types of things, it might be beneficial not to bother with the rules and not to so-called mint new IRIs for those things. And the reason for that might be that we are absolutely sure that no one will want to ask for this particular thing by itself. No one will want to link to this thing. And if we are absolutely sure of this, we might not use an IRI to identify the thing. In that case, we will still have an RDF resource, but without an IRI identifying it, and we will call it a blank node. Blank node because it doesn't have an IRI. But because we are in data and we still need to somehow say that, for instance, the lower three statements have this thing as a subject and the upper statement has this thing as an object, and it is still the same thing, we actually need to identify it, but not using an IRI. There is a special notation for this, and that's underscore colon and then some identifier of the blank node, which is valid only in scope of one document or one query result. And if this was a result of a query, for instance, and you ran the query again, you would get another identifier for this same blank node, which, however, is what we wanted to do when we introduced blank nodes. Because if we wanted to for the identifier to stay the same, we should have assigned it an IRI. So these are blank nodes, RDF resources with no IRIs. I already mentioned that there are two versions of RDF. Nowadays, fortunately, the version 1.1 is the most widespread and supported. So we don't have to go into details of the differences of the versions. Suffice to say that nowadays, since 2014, we have RDF 1.1. To recap, it is a graph data model. It is a directed labeled multigraph. It is directed because all the edges are directed. They always go from the subject to the object. It is labeled because all the edges are labeled with IRIs. And it is a multigraph because we can have multiple edges between two nodes or things. Up to now, we mostly talked about the RDF data model, which means how the data is structured as a graph and what types of tools we have to represent the data in the graph. So we talked about nodes, which represent things, edges, which represent connections of those things. We talked about literals, and we talked about language tags and data types and blank nodes. All those things are independent of how they are actually represented in a file or when sent over the network. However, the RDF serializations, which are how the RDF data model is represented in a file or sent over the network, are an integral part of talking about the data models. So now we'll talk about a few of those serializations. And we'll start with the simplest one. And that one is called NTriples. It's called NTriples, and it is really very simple. So if you imagine how you could represent in the most simple way the RDF triples, this would be it. And this means that in the sharp brackets, you'll have IRIs, and you'll basically have 1, 2, and 3 IRIs representing the IRI of the subject, the IRI of the predicate, and the IRI of the object, and then a dot. And there is one luxury, and that is that you can have comments in NTriples, and the comments use the hash symbol. And then another triple starts, so you have an IRI representing the subject, an IRI representing the object, and then we have a literal with a language tag. A literal uses double quotes, and again a dot and a comment. And if we want to represent a literal with a data type, that's the third example. So here we have, again, subject, predicate, and object, which is a literal with the value 2 and a data type, XML schema integer, and again, a comment. So this is it. This is the NTriples serialization, and you can serialize any RDF graph into this serialization, store it in a file, send it over the network. Of course, there are some drawbacks to this representation. It takes a lot of space because all the IRIs are written there in full. They are often repeated. However, it has also some advantages, and the most prominent advantage is that you can send this over the network, for instance, line by line, or you can read it line by line, and you can chunk the file into many chunks and then concatenate it again. So you can split large data files like this. And also you can compress this representation quite well, even using stream compression like gzip, which basically preserves the property that you can chunk it into smaller parts, even compressed. Yeah. So this is the NTriples serialization. It also looks like this for our case, where we have the example with a web page, which was created on some day, and it has two creators in this case, and two labels, one in Czech and one in English. Right, so let's now take care of some of the disadvantages, which will eventually lead us to the turtle serialization, which will be the second of the 7 standard serializations of RDF we will talk about. So the first optimization we already know, and that's prefixing. So the 5 triples you can see on the top of the slide are again represented on the in the bottom part of the slide, however, with prefixes. So first we define the prefixes using the @prefix keyword. Then we name the prefix, and then we state the IRI, which is being named by the prefix, and then there is a dot. We define 4 prefixes like this, and then we use them in the data. So the 5 triples you can see on the top are the same 5 triples you can see at the bottom on the slide. However, they are prefixed. And you can see that already the data is easier to read by people, and it also saves some space because the prefixes are not repeated as full IRIs. Now, if we take a look at the prefix data, there is still some redundancy. For instance, we can see that the subject is the same for all 5 triples, yet it is repeated 5 times. So let's take care of that, and let's introduce a semicolon, which means that the subject is the same as for the triple before that. So like this, we can already save 4 instances of the prefixed IRI, and it again makes the file a bit more human readable, because we can see at first glance that all 5 triples relate to the same thing, which is the web page. And when we take a look at this again, we'll see that there is still some redundancy. For instance, we have 2 titles and 2 creators. So let's take care of that too and introduce a comma. When a comma is used at the end of a triple, it means that the subject and the predicate stays the same for the next triple, and we only specify the object, which is different. Like this, we also we again saved some space and made the file a bit more human readable. Now let's talk a bit more about prefixes. The prefixes can be named with an empty string, which is the case of the second prefix. So the second prefix, which you can see as just a colon, is actually a full-fledged prefix just named with an empty string. So this is used or it is used typically in data for some most commonly appearing IRIs, for instance. Another thing I wanted to mention is that you can use the prefix with nothing after it, and in that case it represents the IRI of the prefix. And we can see combinations of these two prefixes or types of handling of prefixes in the 2 triples that we have in the slide. So we have foo bar, that's the typical foo prefix and bar after it. Then we have the foo prefix used as a standalone, which represents the IRI of the foo prefix and nothing after. And then we have just a colon, which is the usage of the unnamed prefix with nothing after it. So again, it's exactly the IRI of the unnamed prefix. Then of course we can use the unnamed prefix with something after it, and so on. So all the combinations are admissible, and this is just to prepare you for the eventuality that you come across such a thing. Or maybe you will want to use these yourself. Now, we need to talk about relative IRIs. These work the same as, for instance, relative paths in your file system. So sometimes it is not convenient to state always the full absolute IRI, starting with HTTP and so on. Sometimes it is best to define what is called a base, which is the start, or I don't want to use the word prefix because that means something else, but it is the common start of all the IRIs used, and then you can just use what's different or what's in addition to the base as a so-called relative IRI. So the 3 IRIs in the top left part of the slide are all relative IRIs because they don't start with a scheme and a colon, like HTTP colon. That's how you know those are relative, and they are relative to what is defined as a base. So let's have an example. We'll have prefix foo, and then we'll have a base defined as a http newbase.com/. And then what is important is what happens when there is no base defined, which is the first case. The first case, in the first case, you can see hash document. It is a relative IRI, but at that time, there is no base defined in the file. So in that case, you take the document URL as a base. If you want to define the base explicitly, you can use the @base keyword and define it explicitly. What will happen is that the first triple, even though it looks exactly the same as the second triple, will actually mean something else, because hash document in the first triple has a different base than in the second triple. So it is quite practical if you are going to use relative IRIs to define the base at the start of the document so that it is clear which IRIs are represented like this. Right, there is one specialty in Turtle, which are multiline strings. So if you use triple double quotes, you can use new lines in strings, and those will still be in scope of the literal. With regular double quotes, a new line is a legal character and needs to be escaped. Now there are some characters that need to be escaped in Turtle, no matter the use of single double quotes or triple double quotes. So you need to escape your tabs, line feeds, carriage returns, double quotes, greater than signs and backslashes. And sometimes you may come across a Turtle file which has all the Unicode characters escaped using so-called Unicode escapes, which is /u and then hexadecimal digits. A decent parser will take care of this for you. So when you parse your Turtle file, which uses these Unicode escapes, when you load the file, those will be again encoded normally as Unicode strings. Right, class assignment. In Turtle, there is a special shortcut. It's syntactic sugar, which is the word a. Remember that in our examples, when we talked about the catalog or a page, we said there is a thing which is a catalog, or there is a thing which is a page. And which is a was then named using the IRI RDF type. This orange IRI is the full IRI of this special RDF type predicate. And it is so commonly used that in Turtle it has this replacement word a. It is a because it is read as this is a FOV document. So when you read it as a, and it stands for the RDF type predicate, which you can see in full on the top of the slide. Now there is also a shortcut in Turtle for blank nodes. So you have already seen blank nodes, which are nodes without an IRI, but still with an identifier, which is generated locally for a given document. And you can use that, that's fine, but this can be also shortened. On the left, we have a representation of a V card, which is a card you give to someone when you want to give them your contacts. And this V card has an address specified on it, and this address is a blank node. So we can use the square brackets to say that, or the square brackets in the object part of the triple to say that the object is a blank node and it has the following predicates and objects with this blank node as a subject inside the brackets. And those two notations are then equivalent. There are shortcuts in Turtle for commonly used data types. So without these shortcuts, you would always have to use the double quotes with, for instance, a number, and then the IRI of the data type, which can be prefixed, but still. You can use a shorter notation, which you can see here for integers. So for the number 4, you can just use the number 4 without any quotes in the position of the object. It's the same as +4, and it's the same as if you would use the longer notation with the double quotes and the identification of the data type. The same goes for decimal numbers. So if you have a number with a dot, it will be translated as a decimal number. If you have a number with an exponent, it will be of a type XSD double. And the same goes for Boolean values. So you can use true and false directly. You don't need to use the double quotes and the indication of the type using IRIs. Now, this is kind of a funny example of what can be done with prefixes and relative IRIs in Turtle. So here we'll take a look at this document and we'll try to think about which IRIs are represented by the shortened representation in the document. So we'll start from the top. A1, B1, and C1 are all relative IRIs. At this time, we don't know the base, so it will be the IRI of the document. So this document, when published on the web, it will be published on some URI, and this URI will be the base for those 3 IRIs comprising the first triple. It means that when we take this document and publish it somewhere else, those triples will mean other things. So that's not really practical, but that's how it is in this document. Now, to avoid this, we will define the base to be example.org/ns, which means that the A2 IRI is relative, but now it is relative to this newly defined base. And the same goes for C2, and between A2 and C2 we have a absolute IRI, which has nothing to do with any defined base because it is absolute. Right, so C2 now stands for this IRI. And now we will redefine the base. We can do that, we can redefine bases, and we can redefine prefixes in the middle of a document. It is not recommended, but it can be done. And what we redefine the base with? Well, we redefine it with a relative IRI. So first we need to discover what this relative IRI actually means, and that will be used as our new base. So in this case, it is relative to the lastly defined base, and now the new base will be this. So A3, B3, and C3 will be relative IRIs to this newly redefined base. Now we'll introduce prefixes, and we'll have the unnamed prefix, and the unnamed prefix will be defined using a relative IRI. So relative to what? Relative to the lastly defined base, and this will be used as our unnamed prefix. So A4, B4, and C4 are not relative IRIs, they are absolute IRIs, and they are using the unnamed prefix here. Now we will redefine the unnamed prefix, because we can do that, and we will redefine for simplicity using an absolute IRI. So A5, B5, and C5 are then quite naturally IRIs like this. Well, this was a funny example of what you can do with RDFTurtle and relative IRIs and prefixes, and how you can redefine them in the middle of a document, which I do not recommend because then the data is really not readable. For machines, it's okay because they don't they don't care about this. They have their algorithms and they take care of this for them. But since Turtle is a serialization which is meant to be read by both machines and people, do not do this. Now we'll take a short detour from RDF serializations. We had NTriples and Turtle, and that's a good base. But now let's talk about something else for a bit before we return to serializations. Let's have a statement like this. We have a web page, was created by, and for simplicity, it's a literal Jakub Klimek. Now, what if we want to say something about this statement? We want to say that this statement came from, let's say, XYZ, and it was scraped from that web page on the 23rd of April 2020, and so on. So we want to say some things using statements about this statement. So the question is how to represent this in RDF. Well, if you think about it, there is a small problem, right? In RDF, everything is identified by an IRI. So the subject of the triple is an IRI, the predicate is an IRI, an object, when it is a thing, it is also an IRI. However, the triple itself does not have any IRI assigned. So it is hard to say something about this triple. For instance, some metadata like when it was created and so on. So what can we do? What can be done about this? Well, there is a direct approach called reification, which will solve the problem that I just mentioned, that the triple does not have any identifier, so we cannot have any data about it. And it will assign an identifier to that triple. So when we have the original triple, the page was created by Jakub Klimek. Now we'll have the reified statement where we assign an IRI or a blank note ID in this case to this triple, and we'll say this triple is an RDF statement. This triple has a subject, which is the page. The triple has a predicate, which is created by, and the triple has an object, which is Jakub Klimek. So we basically describe this triple by other triples, with the advantage that now we have the identifier for this triple, for the statement, and we can add more data, like the triple was created on the 23rd of April. So this is one approach called reification. The natural drawback to this approach is that we'll have at least 4 times the triples than before, because instead of 1, we'll have at least 4 saying it is a triple, it has this subject, predicate, and object, and then we'll have the metadata. It is also harder to work with the triples in this way, although some RDF databases support this technique and allow you to view this data as if it was in the original form. But still, it is harder and costlier to work with the reified statements. So there is an alternative. However, as you can see already, the reification is the only way to do this when staying within the bounds of the RDF data model as a set of triples. So if we want an alternative, we'll have to change something. And that something is that we'll introduce the notion of named graphs. So the RDF graphs made of triples that we had up to now, we will name, and name again using an IRI. So now the triples will become quads, RDF quads, which will still have subject, predicate, and object, and then they will have the IRI of a named graph they belong to. So the IRI of the named graph is basically the RDF name of one RDF data model consisting of a set of triples. And we'll have multiple ones. So we'll have multiple named graphs, each will be named with a IRI and will contain the triples. When we take a look at that from the point of view of the data model, the triples become quads because we need to store the IRI of the named graph to which this triple belongs to somewhere, and we will do that by extending triples into quads. So then we'll have named graph like the one on the illustration, then we'll have another named graph, and then we'll have one special graph called a default graph, which will not be identified by any IRI. So when we specify an RDF triple and do not specify the graph IRI, we will say that this triple belongs to the so-called default graph. And this brings us to the notion of an RDF dataset. An RDF dataset is a term defined as one default graph and a set of named graphs, where the named graph is the set of RDF triples with the IRI of the named graph. And now we'll come back from the detour to RDF serializations, because when we extended our data model from triples to quads, we also need to be able to serialize those quads. So the first serialization supporting quads will be named nquads and will be quite a natural extension of NTriples. Just instead of 3 triples three parts of a triple, subject, predicate, and object, we'll add a 4th part to the quad, and we'll have subject, predicate, object, and the IRI of the named graph. So quite a natural extension of the NTriples serialization into nquads. And we'll do the same for RDF Turtle, and we'll name that extension RDFTrig. RDFTrig represents the whole RDF dataset, which means one default graph and a set of named graphs. And what's new is those curly braces, the curly braces which can be prefixed by the keyword graph, and in the sharp brackets there is the IRI of the graph to which the contents of the brackets, which are triples, belongs to. So RDFTrig allows us to not mention curly braces at all. In that case, all the triples belong to the default graph, or we may have explicitly mentioned default graph by the curly braces with no graph IRI, which is the first case in the example, or we may say that those triples belong to a named graph with this IRI, and in that case we'll have the curly braces prefixed with the graph IRI, and optionally to emphasize what this means with the keyword graph. So this is again quite a natural extension to RDF Turtle, and we have RDFTrig, which brings us to 4 of the 7 standard RDF 1.1 serializations. And for today, those 4 will be enough, and now we'll talk about something else. Now we'll talk about RDF Schema, or RDFS. RDFS is a vocabulary. Vocabulary is a collection of classes and properties, the defined IRIs and the definitions, so that they can be used in RDF data as IRIs of predicates and IRIs of classes. And the predicates and classes need to be defined somehow, and RDFS is the way how they are defined. It is actually one of the ways, but it's the simplest one, so that's what we will use in this course. So RDFS itself is a vocabulary. It is a vocabulary for creation of other vocabularies. And we'll start right away. We'll create some classes so that they can be used as objects of RDF type in actual data. So here we'll create a few classes and some class hierarchy. We'll create a motor vehicle, a passenger vehicle, a van, a truck, and a minivan. All those will be of a type RDFS class. This means that we can then use, for instance, xvan as an object of a triple in data where a specific van will be of a type xvan. So we'll say that xvan is a class. Because we are in RDF, xvan in this case becomes the subject, RDF type is still the predicate, and by assigning it the RDFS class type, the RDFS class, which is the set of all classes, we say that it can be used and it will be used in data as a class. And those classes have a hierarchy. So, for instance, a passenger vehicle is a subclass of motor vehicle, a van is a subclass of a motor vehicle, and a truck is also a subclass of motor vehicle. And then there is a minivan, which is both subclass of a van and subclass of a passenger vehicle. So then the hierarchy looks like this, and we can have multiple parents of the subclass of relation. So like this, we can create classes and subclasses. Of course, then in the data, when we have an instance of a minivan, it will have an IRI like my http minivans.org/myminivan1 RDF type x minivan. This will be in the data. But from the knowledge of this vocabulary, we can also deduce that this particular minivan is also a passenger vehicle, a van, and a motor vehicle. So then, when we have a bit smarter RDF database which knows of these relations, we can ask about instances of all motor vehicles, and we will get instance of the minivan. For some simpler implementations of RDF databases, this won't hold, and then we'll have to so-called materialize the hierarchy, and we'll have to say that our minivan number 1 is a minivan, is a van, is a passenger vehicle, and is a motor vehicle for this to work. Right, so now we are able to create classes and subclass of hierarchies using RDFS. So now let's move to properties. With properties, the situation here is a bit different than in object-oriented programming, which you may think about when you see classes and properties. So in RDFS, this is different because properties in RDF are first-class citizens, which means that they stand alone. So you may not have any class and you still can have properties. Well, that's because, as with anything in RDF, you assign an IRI to this property. You say it's of RDF type, RDF property, and that's it. You have a property which you can then use as a predicate in your data. And we'll illustrate this on this example. We'll have a person, which is a class. We'll create a class person. Then we'll have X-author, which will be RDF property. Note that there is one small difference. Classes use the RDFS prefix and properties use the RDF prefix. Now for properties, they are first-class citizens, but still we can specify their domain and range. So for author, we say that author has range person, which means that every time the author property is used, the object will be of a type person. And we'll define a has mother property, which has range female and it has domain person. So every person has a mother and every mother is a female. Now so this property is used to connect things to other things, RDF-wise, so people to females. Now we'll create a property for usage with literals, xage. So again, it's a property, but its range is XSD integer, which means that the values of xage should be numbers. And the same goes for weight. So we'll have weight for which we'll say, right. Now weight is another example on which I want to demonstrate one possible issue with RDFS. So let's see, weight has a domain book. So every book has a weight, right? And now we'll have motor vehicles and we want to say motor vehicles also have weight. So why define another property? We'll use the one we have for books, right? So we'll say that weight has a domain motor vehicle. Now, it might seem doable, right? It might seem that now with a definition like this, we are able to say that we have a book, it has some weight, and we have a motor vehicle and it also has some weight. But there is a catch. Remember what I said about the range, and it goes for domain as well. Whenever you use the property, it means that the object, in case of range, or the domain, in case of subject, is of a type which is specified here as RDFS domain or RDFS range. In this case, it means whenever you use x terms weight property, the subject is of a type book and the subject is of a type motor vehicle, which is nonsense, right? Because then you would have one subject which is both a book and a motor vehicle, which should not happen. So you cannot do it this way because all those statements apply, and then you would say about your subject that it is both a book and a motor vehicle. So you don't want to do that. And with properties as well as classes, we can have hierarchies. So we can have a driver, which is a property. We can have a primary driver, which is also a property. And then we can have a statement that says that the primary driver is sub-property of driver, which means that whenever two nodes, two things are connected using the primary driver property, they are also connected therefore by the driver property. So it is the same as with instances of classes, but here we have the instance of the property is a pair of nodes which are connected using that property. This can be visualized like this. So we have people in the green field and motor vehicles in the yellow field, and then we have pairs of nodes where the first one is a person, the second one is a motor vehicle, and all those pairs of nodes which are connected are represented by the property. So again, the property can be viewed as a set of pair of nodes connected by that property. And in that case, we can have a subset, which is the subproperty primary driver. So if primary driver is a set of pairs of nodes connecting person and motor vehicle, and saying that the person is the primary driver of that motor vehicle, because primary driver is a subset of driver, it also says that the person is a driver of that motor vehicle. So with RDFS, we have hierarchies of both classes and properties. With RDFS, we define the IRI of the class or the property, and we assign a human readable label so that when that class or property is used in the data, we can show it to people, because data ultimately is always shown to people. So we need something else than an IRI, because that is not a human readable label, right? So we need a human readable label for each class and each property, which is assigned using the RDFS label predicate. And whenever we have a label, we also might want to have a longer description, and that one uses RDFS comment. RDFSC also points to a resource that might provide additional information or additional data about a resource used as a subject in that triple. So it is a generic predicate that is used sometimes when we want to point users or readers of our data to other data. And finally, there is RDFS is defined by, which typically points to a document which contains some definitions of the classes and properties we use or we define using RDFS. RDFS also has a support or adds support for collections into RDF. So as I mentioned before, the RDF data model is a set of triples, which means there is no ordering. But what if we want to preserve ordering of things or ordering of some statements? Well, we can use collections for that, and there are two types of collections: closed collections, which we can see now in the slide, and open collections, which we'll get to in a moment. But let's start with RDF list, because this one is actually the most used collection in RDF. It is a closed collection, and if you take a closer look, it is a linked list, which you might know from some basic programming courses. So we have a triple which says, for instance, that a book has authors, and the object of this triple is the node with the red arrow here and with the IRI my list. That's the object of that triple. And that list points to RDF, using RDF first points to the first item, and using RDF rest points to another list. So it's a typical linked list implementation. And also this node has a type RDF list. So all the nodes have type RDF list. Using RDF first, they point to the items in the list. And using RDF rest, they point to the list representing the rest of the list. And the last item is has the IRI RDF nil, which is an empty list. So a typical linked list. It preserves the ordering of things. However, as you can see, it is a bit difficult to work with those lists. Nevertheless, they are used in RDF data. And the RDF list is a closed collection because if you want to add an item, you need to change the whole, at least locally, you need to change the data. You cannot just add another RDF rest or another RDF first predicate to an existing list, because then there would be two, which is invalid. So it is a closed collection. It is not easy to add a triple just by adding to existing list. You need to change the list if you want to add item. The other type are open collections. So they are a bit simpler. Again, we may have a book has author, and the object will be this node with the red arrow identified by my bag. And the items of this collection are connected using the special predicates RDF _1, _2, _3. So like this, you can add all the items into this collection. However, the exact interpretation of this collection is determined by the type of the collection. If it is a bag, then it's a set. So there is no ordering among the items, even though they are connected using _1, 2, 3. If it is RDF sequence, then those predicates should be interpreted as an ordering relation. And if the type is RDF alt, then those items should be interpreted by applications working with the data as alternatives in some way. Interpreted by an application. So it is not set in the data in what way. So these open and the collections are open because you can simply add another item by using RDF _ and the last item +1 predicate to add to this collection without changing the original collection. Right, and RDF list, as I mentioned, is quite used in RDF data, the closed RDF list, the linked list, and therefore in RDF turtle there is a syntactic sugar to shorten the notation of RDF list. So you can have the regular brackets like this, which mean that the object of this triple is a list and the items of the list are inside those brackets. An empty list is empty brackets. Now RDF Schema version 1.1 is also from the year 2014. It is used to define other RDF vocabularies. And one more thing I want to mention regarding RDF Schema is that later when we will talk about XML schema, based on the names of those two techniques, they may seem similar, but they are very different in functionality. Because one term you might see in connection with RDF is that RDF is so-called schema-less. So why we have RDF schema here, right, when RDF is schema-less? Well, schema-less means that the data model of RDF is a set of triples. So you may add any triples you want. In this case, in this meaning, it is schema-less. You don't have any schema telling you what triples can and cannot go into the data. Any triples can, so RDF is schema-less. But then we have RDF schema, which defines vocabularies, classes and properties. But here, the classes and properties are used together with the data to explain the data and to add some meaning to the data, not to restrict the data, as it is in the case of XML schema and maybe other schema languages. So there is a huge functional difference from other schema languages. RDF schema doesn't restrict, it adds meaning, and XML schema actually does restrict what you can do with your XML document, but we will get to that when we'll talk about XML later. Another term we need to talk about with regards to RDF and linked data and the web is something called an open world assumption. This is also different from other data models and how the data in them is interpreted. You see, the open world assumption says basically that, well, what it says is in the slide, right? But what it means is illustrated by the example. Let's say that we have a statement, Mary is a citizen of France. And the question we have regarding those data is Paul a citizen of France? Well, in traditional data models and representations and interpretations of data in them, which is the closed world, the answer would be no. Why? Well, because in the data we have only that Mary is a citizen of France, not Paul, which means we interpret this as Paul is not a citizen of France. However, on the web and in RDF and linked data, we interpret data differently, and that is called the open world assumption. For the same statement and the same question, the answer in open world is unknown, because we do not explicitly have the data that Paul is not a citizen of France. We do not know whether Paul is a citizen of France or not. So simply, because a statement is missing from our data does not mean that the statement is false. We just don't know what the value, the truth value of the statement is. So this is what is called an open world assumption, and it is different from the world of, let's say, relational databases. And this brings us to the term linked data. As always, when we introduce a new term, it is there because it solves some kind of problem that we have. So let's take a look at the problem that we have that we need to solve using the term linked data. And for that, let's take a look at regular non-linked data. We have not talked about CSV or JSON data in detail yet, but I guess all of you have seen a JSON file or a CSV file before. So they typically look like this. And here we have two data sources, two data sets, two files. Each has something to do with movies and actors. And the tabular one basically says something about an actor and a movie. It is not clear whether the actor plays a role in that movie or and the value in the last column is the name of the role, or whether the last column is the name of the movie the actor plays in. It's not clear at the moment. In the JSON file or the hierarchical file, we have some identifiers, a name and a rating. So without any additional information, it is not even clear that it is a list of movies and their rating. It could be a list of roles and some kind of rating and so on. However, this is how typical non-linked data looks like. It's not clear many times what the data actually means. It is missing any kind of link to a documentation, but there are other problems as well. Let's say I want to share some information about what I discovered in the tabular dataset, and I want to say to my friend, hey, take a look at this actor, 1, 2, 3, 4. He's cool, or something like that. And the natural question would be whether this 1, 2, 3, 4 or that 1, 2, 3, 4 in this file or that file. So it is not clear based on 1, 2, 3, 4 where and how to get the data about that entity, right? It's unclear. So this is one problem that we have. We need to say additional information in order for people to be able to actually get to the data and read the data. It is not clear what some of the values actually mean. So for instance here, let's say we do not know check, so it's just a column name. Let me tell you, it means stars, but it's not clear entirely whether it means stars in or stars as. So it is not clear whether this relates the data to a movie or a role in a movie. Finally, when we clear up the meaning and we say, okay, this means that the actor plays in a movie, there is a problem because in the other data set we have movies and IDs, but in this data set we have only the movie name, and incidentally or at the same time we have two movies with the same name in the other data set, and it is not clear to which movie we actually link to. And it is a big difference because one of the movies has a rating of 9, the other has a rating of 5.6, which is a difference. So the problems here are ambiguous definition, identification of entities in data, and we already know what leads to solving this problem because we already talked about identifying entities on the web using IRIs. Then there is a problem of low findability and accessibility of data because based on the traditional identifiers, we know nothing about where the data is and how to get to it. And again, this is a hint towards IRIs and URLs. And finally, there is no contextual information. So there was lots of information about those files that I had to tell you. What links to what means what, and so on. And there is no link from the data to the explanation. So again, a hint towards URLs. So when we have a set of problems and we want to solve them, basically it means that we will have additional requirements on the data, so that we don't come. It doesn't come to this problem, to these problems. So what we need is a global and unique identification of entities in the data. We need to be able to find and access the data based on these identifications. And we would like to have some contextual information as well. So when we find the data, it would be nice if the data pointed us to other data, or maybe the documentation of the data, which explains its meaning. And the question is there such a system that would allow us to do that would solve those problems? Well, the answer here is there is, but not for data. There is for documents, and it's the World Wide Web that we all use every day nowadays. And it is built on top of a few simple principles. HTML as a format for publishing documents, URLs as unique global identifiers of documents, HTTP as the protocol that helps us with localization and accessing the documents based on their URLs, and finally hyperlinks between documents. When we find one document, it links to several others that provide us the context, the contextual additional information. And on this web, we have basically two types of applications: web browsers, which humans can use, and search engines. What search engines allow us to do is that we do not have to necessarily know the URLs of web pages we want to access. We may use a search engine to search in some other ways, and the search engine will give us the URL that we then can access. Right, so with the web, we can publish documents, but only human readable documents. Everyone can view them, the documents, in any browser that is compatible with the standards, if they know the URL, or if they use a search engine. And the documents link to other documents that we might not have known about, and we can discover more things. The World Wide Web was invented by Tim Berners-Lee in 1989 at CERN. Recently, there was a 30th anniversary of the web, and Tim Berners-Lee actually formulated principles of linked data based on what the web was actually meant to be all those years ago, and what it is not at the moment. So now let's have the principles and the state of the web in mind, and we'll go from that to actual linked data. So applying the web principles to data. Here we have 5 different portals, all with information about Prague. The information there is published as documents for people. So if I, as a human, go to all of those portals, I can collect many nice pieces of information and do some analysis on top of that. That is nice, but what if I was supposed to answer a query like this? Let's say money spent in Prague for children playgrounds in the last 5 years and per one child. Well, all the information is definitely on those web pages. However, since those web pages are not accessible as data, only as documents for people, I need to either do the analysis manually, or if I were to aim for answering those questions using a query, then some steps I need to take are there, and those may be quite difficult. So let's now for a moment imagine that we need to answer these queries as real queries, and all we have are those webs with documents. What do we have to do? Well, we probably have to first scrape the data from the individual websites, so create 5 different scrapers, which are tools that basically take an HTML file and download them, and then pick the interesting pieces of data and save it as some structured data. So that's one thing we need to do. Then we need to prepare our database on top of which we will query this data. So we need to create a database schema for that, and we need to create transformation scripts for all the data that we got from the web pages. Then we need to load the data, and then we can start writing the query. So that's a lot of work, right? Especially when nowadays the web pages are typically not built like this. So in a way that would just store a set of documents written by people for people, but they typically look like this. So they sit on top of a database already. Then they encode the data for people, and then we would need to actually scrape the data back into a machine-readable format. Well, the situation is not so bad. It's one step better. Nowadays, when a web is built on top of a database, there is typically a machine-readable API or machine-usable API. So we are able to build mashup applications on top of different databases. But this solves only part of the problem, because we don't have to deal with scraping HTML and parsing HTML, but we still have a set of proprietary APIs. Each is different. Each uses a different format. Each is accessible in a different way. We need to learn all of them, and then we need to load the data into our database and so on, and the rest of the steps is the same. This is also illustrated by this famous image, which demonstrates the problem of data silos, which means that companies like Facebook and LinkedIn and so on compete over the users, and their aim is to get all the users of the other one. So they won't allow you to, for instance, send a message from Facebook to LinkedIn. They will instead force you to contact your friends on LinkedIn and tell them to create an account on Facebook so that you can message them. Or you can create a mashup application, which means that you need to learn as a developer the APIs of LinkedIn and Facebook. Then you need to integrate the friends you have on Facebook and LinkedIn somehow, and then you are able to send them a message in one step. Or you need to create an account on each of those social networks where you have some friends and send multiple messages. So this is not an ideal state at all. And what seems to be the problem? Well, let's take a look at the web of documents as we know it, and the principles it is built on, and the state of the data on the web nowadays. Well, where the web of documents has URLs as the unique global identifiers of documents, there are no global identifiers of things in the current state of the web. There are identifiers of the APIs, but then the things represented in those APIs have proprietary identifiers. On the web of documents, there was HTML as a single format for publishing documents. However, with the current state of the web, there are many formats for publishing data: XML, JSON, CSV, Excel files, and so on. In addition, on the web of documents, HTTP was used for localization and accessing documents using the URLs. And currently on the web, HTTP is used for localization of the APIs, but not for accessing these individual things in those APIs. And there are no hyperlinks between different APIs, or if there are, they are proprietary, not standard ones. So, since the current state of the data on the web does not follow the web principles, it has many problems, as illustrated here. And now the question is, can we apply the principles of the web to data so that we can enjoy the benefits of the web and not just with human readable documents, but with actual data? And this is where linked data comes in, because linked data is a set of best practices for publishing and linking data about entities on the web. It is the application of the proven web principles to data, and it has two goals. One goal is machine understandable and readable data based on the semantic web. And the other goal is providing, so the first goal means explaining properly what is in the data. And the second goal is linking to other data sets published or other data entities published by other publishers, providing context in the same way that you have links from one document to another on the web. The linked data principles are four basic principles that are parallel to those that the web of documents is built on. And I will now illustrate the four principles on examples and why are they crucial and necessary. So, right, the first two principles, they are use URIs as names for things and use HTTP URIs so that people can look up those names. Well, if you imagine that the web of documents, how it would look like if those two principles would be not there for the web of documents, it would mean that you have a web page that doesn't have a URL. So it is very hard to get to, you cannot share it, you cannot point to it, you can't identify it, and so on. So it is clear that it cannot work. However, this is the state of data published on the web today. You have the individual data items, but you cannot point to them. You cannot share individual items, and so on and so on. So let's take a look at what a data publisher needs to do to be compliant with the first two principles. So let's say we have these 6 entities in our data, and we want to publish them as linked data on the web. So we follow the first two principles, and for each of those entities, Prague City, Prague Budget, a public contract, or a EU-funded project, we assign a URI, and we assign an HTTP URI because we want the data to be accessible via HTTP. So we assign these URIs, and we followed the first two principles successfully. Now, other publishers will do the same. So the Ministry of Finance here also has some data about Prague and some other entities, so they will also assign URIs, HTTP URIs to their data items. And the other publishers will do the same. So now you may already see that there seems to be a little bit of a problem with the identification, that the same thing is identified by different URIs in different data sets or in data coming from different publishers, but we will get to that. That is quite a natural state of things. So these are the first two principles. Now the third principle, when someone looks up a URI, provide useful information using the standards, which is RDF and Sparkle. So we already talked about RDF, so we know how the standard way looks like. And if we take a look at the web of documents where the standard is HTML, and think what would happen if actually web pages were written in something else also, it is actually not so hard to imagine, because nowadays it still happens that you browse the web and suddenly, instead of going to a web page with a text that you want to read, you are forced to download a PDF file or a Word file, and then search for application that will open it, and then open it, and inside on your electronic device you see text structured in pages, which doesn't make any sense, and it would be much better if the text was actually just another web page, right? So this is quite easy to imagine, and we know that this state definitely is not ideal. Now there is a little technical detour. When you see a URI, what do? You basically put it in your web browser and you see what happens, and you expect a web page to appear. Now, if we use URIs also for data entities, an unprepared user may use that URI of that data entity, put it in a browser, and be surprised, and not in a good way, that there is no web page, there is just data in RDF, in Turtle in this case. Well, this is solvable because with each HTTP request, you also fill in the accept header, in which you say whether you are requesting an HTML representation of that resource or an RDF representation of that resource. So actually, one resource with one URI can be served via HTTP, both as HTML and RDF. And the fourth principle of linked data is include links to other URIs so that they can discover more things, and they is users. Now, again, imagine the web of documents if that fourth principle would not be there. So you would have this Wikipedia page, and all the blue links that you can see there wouldn't be there. So if you were, for instance, interested in information about the Kingdom of Bohemia, you would have to search for it somewhere else, because the author of the page wouldn't give you the link to the page talking about the Kingdom of Bohemia. So that would be pretty bad, and it would not serve the web as links serve the web today. And the same goes for the data. So data published like this individually is fine, but it is better when it is linked to data from other publishers. Because we already know RDF, we can quite easily imagine how this looks like. It's an RDF triple as any other, but the object is based on a URI of a different publisher, but otherwise it doesn't really matter. So it is just regular linked data in RDF, where from one dataset you can easily link to another dataset, providing your users the context and the ability to download the other data if they wish. Now, there is one special predicate called OWL same as, which says that the subject IRI and the object IRI actually represent or identify the same thing. So this is the solution to multiple identifiers identifying the same thing. When you discover that you have created an identifier, or you just wanted to create another identifier for a thing that already has an identifier, you should link it via OWL same as, so that people or machines reading your data can also see that the entity identified by the other URI is the same thing. And when the data is linked like this, the borders of individual publishers no longer matter. So we'll end up with a web of data that looks like this. And it is similar to when you browse your web pages and you don't think about whose site you are on. You just follow the links and read the web pages. So this is the same with data. And when we compare the principles of the web of documents and linked data, we see that there is now a parallel. So for the web of documents, there was HTML as a single data format. For linked data, there is RDF. URLs identified documents, and now they identify global entities globally. So this is the same. HTTP protocol was used to access documents, and now it is used to access data about things based on their URL. So this is the same. And documents contain links to other documents and entities, and data about the entities contain links to other entities. So this is also the same. What is in addition here are vocabularies. So when we discussed RDFS and how it can be used to create vocabularies, lists of classes and properties, this is something not present in the web of documents, but present in the web of data. Now, if you are wondering where you can find the vocabularies, for instance, those created using RDFS, there is a catalog called Linked Open Vocabularies, where you can go and search for vocabularies used on the web. There is a basic rule when you create linked data, and that is that if someone else created a vocabulary containing a class or a predicate that means the same thing you want to say in your data, you reuse the previously existing class or predicate. Only when such doesn't exist, then you create your own with RDFS and you publish it in this vocabulary so that the next data publisher who comes sees that you have created a vocabulary and can reuse it. Right, so this is linked data. Linked data is a technical interoperability solution. Instead of the data on the web being accessible like this, using a host of protocols and different data formats, it is a bit better. It is all in RDF. It is still accessed using different protocols and in different formats, but it is a step in the correct direction. So if we go back to the example from the beginning, now if all those portals were publishing data as linked data, we could skip all the steps from scraping and parsing and integrating and creating our own database, and we could right away write a query that would answer our question, which was money spent in Prague for children playgrounds in the last 5 years per one child. So this is doable all in one query when the data is published right. And now the remaining question is, can this be successful? Well, in 2007, it started with 12 datasets. The circles are datasets like a dump of RDF triples. The bigger the circle, the more triples in the dataset. And the edges mean that from one dataset to the other there is a link. An RDF link is an RDF triple that has subject from one dataset and object from a different dataset. And the thicker the edge here, the more links there are from one dataset to the other. So, as you can see, there were 12 datasets and this wasn't much. In 2008, there were 32 datasets. In the center, there is DBpedia. DBpedia is a structured representation of Wikipedia data boxes. So if you take a look at a Wikipedia page for Prague, let's say, on the right-hand side, you'll have a so-called data box where you'll have a few structured data items like population and so on. So the people from DBpedia, they scrape those data boxes and create an RDF dataset out of it. And because when you are writing a web page and you are supposed to link somewhere, the first place you look is Wikipedia. With data, it is the same. When you are creating linked data and you want to link somewhere, the first place you look at is DBpedia because there is a page or a resource for almost anything. So that is why DBpedia is so central here. Well, in 2009, there were 89 datasets. Now they are color-coded for individual data domains. So the green ones are publications, the blue ones are database encyclopedias, the yellow ones are statistics, and the pink ones are medical datasets. And so it grows and grows and grows and grows. Here they switched the generating algorithm, and in 2020 we have 1255 datasets in the diagram. And not all the datasets out there make it into the diagram. There are some requirements and you need to register your data manually and so on. But there are some datasets, for instance, from the Czech Republic. Now, there is one more term I want to share with you, and that term is open data. Open data is data which is published on the web and with terms of use that allow you to do whatever you want to with the data. Within, of course, like a legal system, but otherwise whatever you want to. So you cannot, for instance, take a list of addresses and start spamming them, of course, but otherwise you can do whatever you want to with the data. And there is a 5-star classification of open data, where the first star is that the data is technically in whatever data format imaginable, but there are free or open terms of use specified, an open license. Now, this can be a PDF file or a machine unreadable file, as long as it has free terms of use or open terms of use. It is 1-star open data. Now, 2 stars are for data which was structured, being kept structured, so it is no longer necessary to take a screenshot of a table, insert it into an Excel file and save it. Now, if the data was structured to start with, it needs to be structured when published. The 3rd star is for open formats. So we already mentioned what open formats are. So for tabular data, it is, for instance, CSV. For hierarchical data, XML, JSON, and for graph data, it is RDF. Now, with RDF, it is interesting because there is a 4th star of open data, which says when you identify your data entities using URIs, you can have 4 stars. Now, RDF is so far the only data format that natively supports entities identified by URIs. So this basically nowadays means use URIs and RDF. And the 5th and final star of open data is for linked open data, which means that in your data, in RDF, you will have links to other data sets so that the users can decide whether they want to work with the other data sets and get the data without the need for them to search for them, because you provide the links. So it is the same thing as with the Wikipedia page, where the author who wrote that page also gave you the links to other interesting pages. Right. From this, it might seem that when you publish your data as linked data, that's the best you can do. But that's not the case. Publishing data on the web as linked data is the standard. You should do that so that the data is described properly and so that it provides context. But still, this is just a prerequisite for proper data publishing on the web. You need to further think about data quality so that it is easy for other people to work with the data. An illustration here shows that it should be as easy as if, for instance, 4 data sets coming from different publishers but about the same things, for instance, points of interest. So data of high quality is such data when you can work with the data sets from these various sources as if they were just from one source. So that's what is still missing and what is necessary to pay attention to when publishing data on the web. So linked data, a prerequisite for good quality data publishing on the web, but not the final solution.